So in this video we will discuss the notes for section 4.5 on graphing the sine and the cosine functions. So we'll start by looking at a table of values for the graph of the sine function. Well, the purpose here is not to graph a trigonometric function by making a table of values the same way we would do for a quadratic equation, function, or a linear function or a radical function, because we would need special points or key points rather that will give us nice values for the trigonometric functions. And well, those x values are on the top row right here, starting at 0, going all the way to 2 pi, passing through pi over 6, pi over 4, pi over 3, and then pi over 2, and the multiples of the aforementioned special angles that are again pi over 4, pi over 6, pi over 4, pi over 3, and pi over 2, which are 30 degree, 45 degree, 30 degree, and 90 degree angle. No, that's not 30, that's 60 degree rather. Okay, so if we were to plot these points, for instance, let me just do a couple. All right, so the origin, of course, 0, 0, that's the point 0, 0. The point pi over 4 root of 2 over 2, pi over 4 root of 2 over 2. I'm going to skip a few. And then pi over 2, 1. That's pi over 2, 1. And then maybe 5 pi over 6, 1 half. But actually, that one is not over here. That must be somewhere here, right there. Right? That's the pi over 6, which is not labeled in our x-axis, and that's what makes it complicated when graphing this by hand, having to mark the x-axis with all pi's over 3, pi's over 6, and all the multiples in one single period between 0 and 2 pi. All right, well, so we're going to use other techniques to graph this function. So now one of the properties that we have discussed about these trigonometric functions is that they are periodic functions, and in particular the sine function and the cosine function have a period of 2 pi. What does that mean? Well, so let me highlight one of the periods of the graph of the sine function. Well, so it completes one cycle, and then see how let me use a different color. See how the shape of the graph essentially repeats. It repeats in the positive direction, but it also repeats coming from the negative direction. And well, the shape repeats itself every 2 pi. That means it's periodic at 2 pi. Well, as we can see from the graph of the sine function, the domain is all real numbers, and the reason to that is because we don't have any holes on the graph of the sine function, and we don't have any gaps or any vertical asymptotes that will make the graph or show that a discontinuity of the graph. That's not the case. And the range always goes between, it would be worth to draw this line right here. It goes always between -1 and +1. All right. So those are the minimum and the maximum values, and actually those are the values that you can see on the table. See how the minimum value, the smallest value, is -1, and the largest value is +1. That being this -1 and that +1. All right. Now, typically we call these trigonometric functions the circular functions, and well, because where do these values of the trigonometric function come from? Well, surprise, well, that they come from the unit circle, right? In this case, we have we're going to compare the unit circle to the values of the function. Well, so, and rather the graph of the function. So here is what we're going to do. So we're going to start at the positive x-axis right here, and we're going to see actually how, let me use different highlighters so you can see it. So we're going to see how the values for the sine function increase from 0 to 1. Let me actually highlight all this, okay? And that corresponds the increasing from 0 to 1. And we can also see those values on the table. That is between 0 and pi over 2, we have the y values increasing between 0 and 1. And make this bolder a little bit. There we go. Okay. And then number 2, we use a different color for number 2. We use a red for number 2. Okay. So between pi over 2 and pi, the values of the sine function decrease from 1 back to 0. And we can see that right here in the values goes between 1 and 0. They decrease. Okay, so let me make that a little less bolder again. So that'll be the second part of the graph right there. All right, and then the third part of the graph, well, the values actually keep decreasing, you know. Well, so in this case, going from 0 down to -1 for the y values in this case. So that is this sector of the circle, if you will, where the y values go decreasing from 0 to -1. So we're going to go from 0 down to -1 like this. Okay, and then we can see that in the table of values right there. We can see all these values going between 0 down to -1. And the last sector for the graph, that'll be, what's that? We use blue. Okay, so now we're gonna have another increasing set of values between -1 and 0. That is like this. Let me fill in the sector, and that is, you can see it goes increasing between -1 all the way up to 0. All right, and we can see that also on the graphs. I mean, on the table of values, where they go between -1 and 0. All right, well, that being said, well, what else do we have? Well, the graph, of course, of the cosine function, but I'm not going to do the circular approach. I mean, this is, I'm just going to give you all these values of the tables, and simply the values of the table, the function values corresponding to the cosine function. So what we really want to get out of this is number 1, that the period, again, for both of them, it's what's that? It's 2 pi. And then look at the shape. Also look also at the shape of the graph. Well, what color did I use? Okay, so for the cosine function, over one period, it looks like this, between 0 and 2 pi. And then, of course, the graph repeats itself. That is because it completes one period, then a second period to the right, another period to the left. Of course, well, due to the limitations in the screen right here, I can't do more periods, but we can always imagine this with more and more periods. And again, the domain and the range of the function, it's also -1, -infinity to +infinity for the domain, and -1 to +1 for the range. Now, when it comes to graphing trigonometric functions, we're going to do this by means of key points. Okay, let me erase all this so I can actually, well, I can't erase the lines right there. So the key points are going to be the following points. Let me use yellow. Let me use yellow for the key points. The key points, that's the origin, 0, 0. The maximum point, that is the point. Okay, let me 0, 0. Let me label that. The maximum point, which is pi over 2, comma 1, and then another x-intercept, which is pi, comma 0, and the minimum point, which is 3 pi over 2, comma -1, and lastly, the point where the graph of sine completes one cycle, that is 2 pi, comma 0. So we will use these 5 key points as a means or as a basis or something, you know, to graph other trigonometric functions with that will suffer some translation, some shifting, some shrinkings or expansions, as you will see later. For the cosine function, the key points that we will use in this case are going to be slightly different. Well, so the points we're going to use Let me label that is the first point that corresponds to the point 0, 1, the x-intercept that corresponds to pi over 2, comma 0, the minimum point which corresponds to pi, -1, and 3 pi over 2, and then 3 pi over 2, 3 pi over 2, comma 0 again, and the last point, that is the point where the graph of the cosine completes one cycle, that is 2 pi comma 1. All right. Well, so these are not points that you have to memorize, but I mean, after some practice, you will be memorizing these values. What you really, and well, they're easy to come up with by simply looking at the shape of the graphs. So, what are the differences between the sine function and the cosine function, even though their overall shapes look exactly the same? Okay, let's have a look at those differences. Number one, while the cosine function, I mean the sine function, starts at the origin 0, 0, increases, decreases, and increases again, the cosine function starts at the point 0, 1, decreases, and simply increases again. All right, so that's the shape, and from the shape you can always divide the interval between 0 and 2 pi into 4 pieces, and that's going to give you the pi over 2, the pi, and the 3 pi over 2. All right, well, so what are these characteristics of these graphs of sine and cosine? Well, so um, we have in a way already mentioned some of them. The domain, which is all real numbers, that is -1 to 1, negative infinity, positive infinity. The range, which is -1 to 1. The period of this function is 2 pi. Again, that's the value in the x direction where the graph completes one cycle. Now, again, the differences, the geometric or graphic differences between the sine function and the cosine function. The sine function is symmetric with respect to the origin, which means it's an odd function. Let's go back and verify that. All right. So for an odd function, look at this point right there. Okay. That's the point -pi/2, comma -1. Compare this point. Okay. So let's compare this point pi/2, 1 to -pi/2, -1. Both points have the same x coordinates and y coordinates, except that they are opposite in sign. Using the definition of an odd function, this is actually saying that f of negative x equals to negative f of x. All right. And well, what about the even function that occurs when f of negative x equals to f of x? All right, what about that even function? So when we change the sign of the x coordinate, we get the exact same y value without changing its sign. And you can see that here, for instance, well, like the point pi/4, comma, so pi/4, comma, root of 2 over 2, which in the opposite sign, on the opposite side, negative pi/4, comma, root of 2 over 2. Well, this tells us that the graph is symmetric to the y-axis. That's what makes an even function, all right? So now the two graphs differ by a horizontal shift of pi/2. Well, that's why that was by the definition of the complementary function. Remember, sine and cosine, I mean the prefix co for the cosine function means complementary sine function. What do we mean? That is, complementary means, again, when the two angles add up to 90 degrees. So that's why we have this shifting of pi/2 related to that difference of 90 degrees in between them. All right, well, let's get started with graphing basic trigonometric functions. That is, graph trigonometric functions of the form y equals a sine x and a cosine x. All right. Well, one thing to recall from college algebra or from intermediate algebra, where you cover all of these shiftings and transformations of functions, it's that every time you multiply a function by a letter a, um, that's actually a vertical stretching if the number a, the absolute value of the number a is greater than 1, or a vertical shrink if the number is in between 0 and 1. All right. However, if the number is negative, okay, that actually reflects the graph across the x-axis, all right? Or another way to say this, in a more informal way, this flips the graph upside down. All right, that's what it does. Flip the graph upside down. In other words, now, because we're going to use key points to graph these trigonometric functions, so this multiplication by a, what does that do? So let's write it down in summary. So for all points in f of x, multiply the y coordinate by a. We're going to see this in action actually with the first couple of examples that we're going to do. Actually, I'm going to show you the calculations by hand. However, I'm not going to graph the functions by hand. I'm going to use GeoGebra to show you the graph of these key points, the graph of the parent functions, and the graph of the shifted function or the transformed function. All right, so for example, number one, let's graph the function and identify the key points on one full period. Okay, guys, so here's the thing. So every time we graph these trigonometric functions, oftentimes we are expected to graph only over one full period. If you use a graphing calculator such as the TI-84 or any other calculator, it's actually hard to make the graphing calculator graph only one period. It would graph infinitely many periods in the window that you set for your calculator. On the other hand, well, the GeoGebra application that I'm going to use to graph this function doesn't do that. Actually, there is a way to make it graph only one period. I'm going to show you how I do that. Well, number one, let's do all the work by hand. And then we're gonna go to the graphing calculator. All right, I mean to the GeoGebra app. All right, so number one, example number one, we call this a rather than 1 and b rather than 2. All right, so y equals to 3 sine x. Okay, so in this case, a equals to 3. In this case, this means multiply the y coordinates by 3. All right, what y coordinates? Okay, I'm going to go to the sine function. Remember the key points on the graph of sine function? Well, not that you're expected to memorize at this point, but again, after practice and after doing a lot of this, you will be able to come up with these points. The origin, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. Okay, let me scroll this down back to where we were, and let me write down those points. That is, the point 0, 0, the point, comma 0, pi over 2, comma 1, comma the point pi 0, and the point 3 pi over 2, comma -1, and lastly the point 2 pi 0. Okay, well, actually I think I'm gonna need some space for later. Let me make this a little smaller. All right, well, so the 3 in front of the sine function states the a, which is asking us to multiply the y coordinates by 3. Let me let me specify that here. Let me denote it rather. Times 3, only the y coordinate. See how I'm writing this times 3 on the y coordinate only? Times 3 times 3. All right, so we're going to get a whole new set of points. This whole new set of points where the x coordinates remain the same, 0. 0 times 3 for the y coordinate, it's still 0, comma. Pi over 2, which remains the same, comma 1 times 3, which results into a 3, comma. Pi, which remains the same, comma 0 times 3, which is still 0, comma 3 pi over 2, comma negative 1 times 3, which is negative 3. Okay, and lastly 2 pi, comma 0 times 3, which is still 0. So I'm going to graph these 5 new key points, which are the points of the transform sine function by multiplying by 3. All right, so I'm going to go to GeoGebra to show you those graphs of the two functions. So that is the parent function, which is y equals to sine x, and the transform function with the coefficient 3. Alright, so here we are in GeoGebra where I have typed everything already. Well, number one, here in the first line, I have typed the function sine x, and notice the inequality here inside the parentheses. That's actually the window in the x direction where I want to see the graph of the function. That is over 1 period. What is this 6.28? That's actually the 2 pi, because 3.14 is pi, 2 pi will be approximately 6.28. Let me show you the graph. All right, so that's the graph over 1 period. And I have also typed the key points. 0, 0, that's point A, pi over 2, 1, which is point B, pi 0, which is C, 3 pi over 2, negative 1, which is D, and 2 pi 0, which is point E. All right, number one. How did I type this function? Well, I'm going to show you at the end of the example how did I do everything. Okay, so now I'm going to graph the function 3 sine x over 1 period 0 to 6.28. Okay, so that's going to give us a function that is actually stretched vertically by a factor of 3. Alongside, I'm going to input the key points. Well, the point 0, 0 remain the same, so you will see an overlap right here. The second point, pi over 2, comma 3, that's the maximum point. We got all these points by hand. Pi 0, it's the same. 3 pi over 2, negative 3, which is point I. And lastly, j, 2 pi 0, which is exactly the same as the point E, 2 pi 0. All right, so here is the thing, guys. Let me just show you a few technical aspects of how to go about GeoGebra. Number one, you can't simply type f of x equals sine x the way it is here. So let me show you. Let me type another one right here. So for instance, what if I want to type say I would like to go I'm gonna type function. Okay, function, and then I'm gonna choose the second command, that is where you type a function, you have a starting x value and an end x value. I'm going to choose this function, and then I'm going to type the same function I did before. So I'm going to go 3, and then I'm going to go f of x sine, and I'm going to type x for this one. And then I said I wanted to start at 0. Okay, and I'm going to continue all the way to what was that, to pi. Everything is right there, and simply click anywhere, and that's going to type this format for you. So I'm just going to hide it because it's actually overlapping with the actual function here. All right, now that's how you would type functions bounded to a given limit of, or a given interval of values of x. Now, typically when you open GeoGebra, it's going to give you a grid with integer values. If you zoom in a lot, actually it might give you decimals. Notice how the marks for the bolder lines boulder lines on the grid are in the x direction multiples of pi over 2. Pi over 2, 2 pi over 2, which is pi, 3 pi over 2, and 4 pi over 2, which is 2 pi, rather than having integer values. How do you change values from multiples of 1 to trigonometric values? Well, you go here in the gear right here for the settings, and for the x-axis, click on the x-axis, click where, make sure the distance right here is checked. I'm gonna uncheck, and you will see the 0.51, 1.52, 2.53, etc. I'm gonna click distance to my preferred value. Well, in this case, you will have some by default. I already did the pi over 2. So later you would have to input pi over 8, pi over something, etc., pi over 4 to look at other marks, for other shiftings. Okay, and then for the y-axis, I was very specific that my distance is simply 1 right here, 1, 2, and 3. I don't need fraction values, as we're not graphing fraction values in this case for the y values. That's gonna happen in the next example. All right. Okay. Let me finish this. Okay. Let's go back to the notes. All right, so back to the note. Now we're asked to graph the function y equals -1/2 cosine of x. Okay, so number one, let's explain the transformations to the graph of the cosine function, the parent graph cosine function. So number one, so believe it or not, there's two transformations going on right here. Number one, multiplication of the y coordinates by a half, and this negative, which is a reflection across the x-axis, or in other words, flip the graph upside down. All right, well, so let's write that in words. So number one, so a equals to -1/2. This means multiply the y coordinate by -1/2. All right, so I'm going to start with a fresh set of key points, but this time for the cosine function. In the previous example, letter A, we used the key points for the sine function. So let me go back and look for the key points for the cosine function. That is these values 0, 1, not this one, 0, 1, pi over 2, 0, pi -1, 3 pi over 2, 0, and 2 pi 1. Let me write down those key points. Okay, so that is, okay, let me write them down. 0, 1, 0, 1, pi over 2, 0, and what else? Pi -1, and 3 pi over 2, 0, and lastly 2 pi 1. Okay, so what are we going to do? Again, I'm going to denote this multiplication of the y coordinate times -1/2, right? Times -1/2. This guy times -1/2 times, so the x means multiplication, times, it's not the variable x, and lastly times -1/2. All right, so let's perform these operations right here. Okay, so 0, 1, okay, 0, which remains the same, comma, 1 times -1/2, that's a -1/2, comma, pi over 2, which remains the same, comma, 0 times -1/2, which remains 0. Then pi, which remains the same, and -1 times -1/2, careful, negative times a negative equals to +1/2, 3 pi over 2, comma, 0 times -1/2, which is still 0, and lastly 1 times -1/2, so the 2 pi remains the same, and that's -1/2. Okay, so those are the key points of the transform function, which I'm going to show you in GeoGebra how they look like. All right, so here we are in GeoGebra. I'm going to show you the graph of the transform function g of x equals to negative 1 half x. First, I'm going to start off by graphing again the parent function cosine over 1 period. Again, look at the labels of the x-axis. They're multiples of pi over 2. The key points, okay, they're properly labeled and also plotted on the graph. All right, well, let's have a look at the graph of the cosine. So now you have to imagine the graph of this function, or this same graph, shrinked by a factor of a half. All right, so actually, in my marks right here, I should go to the settings and have the distance to be, let me see if I can, I don't think I will be able to change the, so I need the, anyway, so yeah, I don't have the keyboard function. Anyway, so this will be the graph. So that is shrink by a factor of a half, and it's also upside down because of the negative. Let's also plot the key points, okay? And that is the graph of the second function in the example. Now let's go back to the notes, all right? So back to the notes right here. So here I just did the calculations of the new points for given the transformations that we do on the graphs, but I didn't do the graphs by hand. So because otherwise it would be a little hard to do that, and especially when we get to horizontal shiftings and vertical shifting, these get to be harder later on. All right. Let's have a look at another kind of transformation. So graphing y equals to a sine bx and y equals to a cosine bx. So now notice that unlike the previous examples, here on top of having this a's in the coefficients, now we have these coefficients b's inside the angles of the trigonometric function. So these represent a horizontal compression if the number if the number b is greater than 1, or a horizontal stretching if the number b is a fraction between 0 and 1. And well, we can see that because, so for the parent graph, so in this case we have the parent graph of sine over 1 period. That's the one I'm highlighting right now. All right. Well, and there's a period of 2 pi as usual. However, the graph of the sine 2x, which has a period pi. All right. Well, that means it completes one cycle. That one cycle I'm actually highlighting here. When does that occur? When x equals to pi. So what's going on? How can we interpret this? Well, number one, the graph, we can interpret this by the fact that y equals sine 2x complete only one cycle. At the same time, the parent functions complete half a cycle. Or we can also say that when the sine function, the parent function, completes one cycle, the transform function completes one cycle, 2 cycles. That's going to be a better interpretation. So the number 2 right here tells us 2 cycles as opposed to 1 cycle, right? What about the case where we have a fraction instead? So right here, the transform function will only complete half of a cycle in the same amount of time, where the parent function completes one full cycle, right? Okay, so that means 2 cycles of the parent function are equivalent to 1 cycle of the transform function. Well, let's graph some of these examples, but before graphing this, let's let's explain what do these b's do on the coordinates of the point. So the letter a, again, in front of the trigonometric function, actually multiplies the y coordinates by a. However, and as you may recall from either college algebra or intermediate algebra, when we are multiplying the x by a number, we are supposed to divide all x's, all x coordinates by the number b. All right, that's what this b represents. And of course, we're going to see this in action with the examples. But number one, notice that when we are multiplying an angle or an x by a number b, that actually, do you see how that changes the period here? Well, so there's an inequality. We're going to explain this by means of an inequality. Okay, so what's the whole deal about? So number one, the period of the functions y equals sine and y equals cosine. Well, we already know that period equals to 2 pi, all right? At this point, I think it's a good information to keep in mind. Now, again, that is when the graphs show one complete cycle, that is in the interval 0 to 2 pi. All right. So to determine the comparable interval for one complete cycle of the graphs sine bx and cosine bx, for b being positive for now, actually we will rewrite this cycle, this period, in terms of an inequality by replacing x with bx. And let's solve the compound inequality for x. That is, I'm going to divide the three sides of the inequality by b, and this will be 0 over b. That's still 0, less than or equal, the b's go away, x less than or equal to pi over b. And actually, this looking at this inequality, this is the derivation or the proof, if you will, to determine that the period for the period p or the period formula equals to 2 pi over b. That in case you have done this before in high school or something, they might ask you to memorize the fact that p equals to pi over b. That's how you get the period of the sine and the cosine function. Well, all this is summarized in this definition box below. That is, so for the functions y equals a sine x and y equals cosine x, and b being greater than or equal to 0, well, actually there's a little typo here, so you might want to fix your notes. So this should have read y equals a sine bx and y equals to a cosine bx. So I forgot to type the b. All right, well, so actually this number a in front of the sine function, which represents a vertical stretching or compression, has a special name in the world of trigonometry. It's called the amplitude. And the number that multiplies the x is related to the period by dividing 2 pi over b. All right, so now, if in the case that you have, for instance, a function y equals to 3 cosine or sine of x, I don't know, cosine of a negative angle, negative 5x, you would need to use the even and odd properties. That is, for cosine, the negative disappears, but for the sine function, the negative goes outside in the front of the function. Well, that's something we're going to get to do more in detail later. All right, so what are we going to do right here in summary in terms of operations? Again, we will divide. So for letter A, so A means to multiply the y coordinate by A, and B tells us to divide, on the other hand, the x coordinate by b. All right, that's what we're gonna do. All right, now that let's have a look at a couple of examples. So given f of x equals to 4 sine 3x, identify the amplitude and the period of the function. All right, so number one, the amplitude, okay, the amplitude, which is a, okay, let me do let me use it in words first. Okay, so amplitude, which is found by taking the absolute value of a, where a equals 4, that is absolute value of 4, which is positive 4. And for the period, p equals to 2 pi over b, which equals 2 pi over the number 3. So this means that the graph will complete one cycle in the interval 0 to 2 pi over 3. All right. So actually, how about we set that up as an inequality? So interval. Let me actually make some space even better like this. So the interval for one period, that'll be 0 less than or equal to 3x, right? Less than or equal to 2 pi. Divide the three sides of the inequality by 3 to isolate the x and leave it in the middle, 0 to 2 pi over 3. This is key because when we graph the function, you'll see what's going to happen. All right, well, so because we're graphing a sine function, again, I'm going to start with a fresh set of key points for the sine function. I'm not going to scroll this up to copy them again. I'm just going to write them down. That is 0, 0, the point. Well, I'm going to make them a little bigger. So because I'm going to do something. 0, 0. Pi over 2, comma 1, what else? Pi, comma 0, 3 pi over 2, comma negative 1, and what's next? One more, 2 pi, comma 0. Okay, so, well, in this case, what are we going to do for the key points? Well, number one, a, which means multiply the y coordinate by a, which is 4. So the y coordinates get to be multiplied by 4. I'm going to times 4, times 4, times 4, and times 4, and one more times 4. And for b, divide the x coordinates by b, which is 3. And in this case, I'm going to denote division by 3, division by 3, division by 3, division by 3, and one more division by 3. All right. Okay, so I'm going to come up with a new set of points based on the operations I did here. So 0 divided by 3, that's still 0. 0 times 4, that's still 0. Pi over 2 divided by 3, that's actually the same as multiplying by a third, which equals pi over 6. Okay, 1 times 4, that equals to 4. Pi divided by 3, that's pi over 3, comma 0 times 4, which is 0. And 3 pi over 2 divided by 3, that's the same as saying, let me do some side work so you can see it. So 3 pi over 2 divided by 3, it's the same as multiplying by 1/3, where the 3's go away, leaving us with pi over 2. Okay, and what's next? That is, let me erase all this, negative 1 times 4, that's negative 4. And lastly, 2 pi divided by negative 3, that is, I'm divided by positive, not negative 3. So that is 2 pi over 3, 0 times 4, that equals to 4. So these are the key points of the transform function given in the example. All right, let's go to GeoGebra to graph this function, and I'll show you how will that look like. All right, so here we are in GeoGebra, where first of all, I'm going to show you the graph of the parent function, sine of x, and the key points. Now I'm going to show you the graph of the transform function for sine 3x, which will number one, actually notice how the period, rather than having 0 to 2 pi here, which is a 6.28, I'm using this inequality 0 to 2 pi over 3, which is what we have on the notes right here, that interval for one period, which is important to take into account. So you will see this graph right there. All right, it's kind of, let me zoom in so you can see this better. Okay, so well, let's plot the key points: 0 0, pi over 6 4, pi over 3 0, pi over 2 negative 4, 2 pi over 3 0. So those are the 5 key points on the graph of the shifted function, right? On shifted, well, transform function. All right, so let's go back to the notes and look at another example. Okay, so back to the notes. So we are in example number 3. Now we're going to work with a cosine function. That is f of x equals to 2 cosine of 4x. They're asking us to identify the amplitude and the period. And of course, I'm going to show you the inequality that will give us one the interval for one period. Okay, so number 1, amplitude, which is the absolute value of a, in this case a equals to 2 and b equals to 4. So absolute value of 2 equals to positive 2, so it's the same. So for the period, which is 2 pi over b, that equals 2 pi over the quantity b, which is 4, but this one actually reduces to pi over 2. All right, now you might want to write that inequality that represents the domain in for one cycle, that is the interval for one period. All right, that will be, okay, starting 0, between 0 and 4x and 2 pi. And let's divide both sides by, the three sides by 4, and that's going to be 0, x, 0, pi over 2. So that means this graph will complete one period in the interval 0 to pi over 2 in comparison to the parent graph, which completes it in in 0 to pi over 4, and 2 pi rather. Well, in other words, this 2 cosine 4x will complete 4 cycles in the interval 0 to 2 pi in comparison to the trigonometric function cosine, the parent function cosine x. All right, again, I'm going to start with a fresh set of values for the cosine function. What values? Points, the key points. And the key points for the cosine function, again, they are 0 to 0, 1, and pi over 2, 0, pi negative 1, what else? 3 pi over 2, 0, 2 pi, negative 1, no, positive 1, all right? So, again, for a, we will multiply the y coordinates by 2, so times 2, times 2, times 2, times 2, and another one times 2, right? For b, divide by 4. Divide the x coordinates by 4. So either divide by 4 or multiply by a quarter. That's fine. Well, I'm still going to do the division by 4. Division by 4. Okay. Divide by 4. Divide by 4. Divide by 4. Okay. So let's come up with a new set of key points right here. So number 1, for the point 0, 1, 0 divided by 4, it's still 0. 1 times 2 equals to 2. For the x coordinate, pi over 2 times a 4, that's pi over 2 times 1/4. It's multiplying by a fourth. It's the same as dividing by 4, which will result into pi over 8. 0 times 2, it's still 0. Pi divided by 4, that's actually pi over 4. Negative 1 times 2, that's negative 2. 3 pi over 2, okay, let me write this one down. 3 pi over 2 divided by a 4, it's the same as multiplying by 1/4. And that is 3 pi over 8 divided by 0 times 2, which is 0. And 2 pi divided by 4, so 2 pi divided by 4, that reduces to pi over 2, which is the same value right there. So pi over 2 times 2, because 1 times 2 equals to 2. Okay, let me erase all this. So these are the 5 key points for this transformed function. Okay, so let's go to GeoGebra and graph this function. Okay, so here we are in GeoGebra to graph the cosine function and the transform function. Again, I'm going to show you the graph of the cosine function in this case. With the key points plotted. Notice this graph is going to look slightly different because notice how I had the marks pi over 4, pi over 8. I have a bunch of graphs right here, and that's because on the notes we came up with pi over 8, pi over 8, 3 pi over 8. So we need all this. So let's look at the graph of g of x equals 2 cosine for x in the interval 0 to pi over 2. Where did we get this interval? Again, from the notes, that's the interval to graph one period of the function. That is by setting whatever is the angle, which is 4x greater than or equal to 0 and less than or equal to 2 pi. Solving the compound inequality for x, we get this interval 0 to pi over 2. Right? Let's graph it and see how does that look like. Oh, look at that. That's just a very tiny graph actually. And well, let's plot the key points. 0, 2, pi over 8, 0, pi over 4, negative 2, 3 pi over 8, 0, and pi over 2, comma 2. All right. If we wanted to plot more points, all we need is to change this interval to from 0 to 2 pi. But for some reason I can't. It doesn't. Oh, here it is. I can't edit. I can edit this to say 2 pi, and I'm gonna go simply click enter, and now you will see, so not only one period, so that's 1 period, 2 periods, 3 periods, 4 periods. In the same amount of time the parent graph completes 1 period or 1 cycle, right? But yeah, you want to go back to the 1 period maybe. So let me edit the, let me edit back to, what was that? Pi over, let me erase this, and that's pi over 2. Okay, so click enter, and that's just going to give us 1 period, which is all that we want. All right, so let's close GeoGebra and get back to the notes. All right, so back to the notes. We're going to look at the fourth part of the notes, that is graphing the functions y equals to a sine bx minus c plus some d, and y equals a cosine bx minus c plus some d. Well, so in this case, we're going to have all kinds of shiftings and transformations. Well, let's recall what the type of transformation to a function f of x in the form of y equals f of x minus h. All right, so whenever the number is greater than 0, that is x minus 4, x minus 5, or x minus 7, that's actually a shifting to the right, while if the number is negative, that is x minus negative 3, which is x plus 3, for instance, or x minus negative 4, which is x plus 4, that actually shifts the graph to the left, something you might recall from either college algebra or intermediate algebra. All right, so what is that going to do? Well, that's actually the horizontal shift for the trigonometric functions, which in a more fancy way in the world of trigonometry, that's known as the phase shift. Okay, so Actually, when we have all kinds of transformations, these new graphs will suffer both a change in both the period and also a horizontal shift in it. All right, now here is where the graphing utility, especially GeoGebra, will come into play, because to be honest, graphing this by hand may not be an easy process. Well, so to come up with an interval for one single period, which may be a little tricky these times. Well, so again, we want to set this b minus c, you know, the bx minus c, bounded between 0 and 2 pi, and solve the inequality, the compound inequality for the variable x. All right, so add c to the three sides of the inequality, and then that's going to leave us with c less than or equal bx less than or equal 2 pi plus c, and then divide the three sides of the inequality by b. That's going to leave us with c over b less than or equal x less than or equal 2 pi plus c divided by b. And of course, this is not an inequality that I encourage you to memorize. So actually, we're going to set up an inequality for every given example, for every given case. Well, so let's prepare for a more in-depth analysis of of the graph of a trigonometric function. Well, so number one, okay, given f of x equals to 2 cosine of 4x minus 3 pi plus 5. Well, they're asking us to identify the amplitude, the period, the phase shift, and the vertical shift. So we're being asked to do a lot more for every one single example. So, okay, so number one, first things first, the amplitude, which is the absolute value of A, which is the absolute value of 2, which is 2. And then the period, P, which is 2 pi divided by B, which is 2 pi divided by the value of B. Actually, it would be worth if we label our numbers A, B, C, and D. So dividing by B, which is what? 4. That equals to pi over 2. Okay. And then let's find the phase shift. To find the phase shift, set the angle equal to 0. All right, I need to use word. Equal 0. That is, the angle is all this expression. I'm going to highlight it with the same color, blue. That's the angle, 4x minus 3 pi. All right, so phase shift. Phase shift. That is 4x minus 3 pi equals to 0. That means 4x equals to 3 pi. And dividing both sides by 4, we're going to get x equals to 3 pi over 4. Well, since in this case we got a positive result for x, well, the negative tells us that it's going to be shifted to the right. A positive inside of parentheses would have been to the left. Well, here means this is shifted 3 pi over 4 units to the right. All right. Okay, what else are we going to do? Interval for one period. For the interval for one period, I'm going to bound the quantity 4x minus 3 pi greater than or equal to 0 and less than or equal to 2 pi. So number one, let me use a different color. Let's add 3 pi to the three sides of the inequality. That's going to leave us, okay, plus, 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 and that equals 3 pi less than or equal to 4x less than or equal to 5 pi. And then divide the three sides of the inequality by 4. And that is 3 pi over 4 less than or equal x less than or equal 5 pi over 4. So that means this graph with all of these shiftings and transformation will show one period of its shape in the interval 3 pi over 4 and 5 pi over 4, as we will see in the graphing utility for GeoGebra. All right. Well, so what else can we do? Okay, so this plus 5 right here, which represents the vertical shift. Okay, represents the vertical shift. All right, okay, so here's the thing. As a side note right here, I would like to be more specific. So, amplitude, so note, amplitude and vertical shift will affect the range of the function. Right, will affect the range of the function. Well, so what are we going to do? So number one, so again, amplitude, which happens to be 2, and the vertical shift, which happens to be 5, that will affect the range of the function. So in this case, we're going to do two operations. Remember what do we do for the multiplication by 2? We do multiply by 2, of course. And the plus 5, which is the vertical shift, which is adding the 5. So how are we going to manage this, the graph of this function, or rather the range of this function? So number one, I'm going to start with a fresh range. Remember the range of the cosine function? Isn't that -1 to +1? Okay. Now, there are two operations that we're going to do to modify the range. That is one described by the amplitude and the other one by the vertical shift. But which one do we do first? So, do we do the addition by 5 first, or do we do the multiplication by 2? So, guys, this is key right here. The key right here is to use PEMDAS anyway. So yes, we have a multiplication by 2 and an addition by 5. By the order of operation, the multiplication goes first. Okay, so multiply both endpoints of the range by 2 times 2. Okay, let me use a different color. So that is times 2 times 2. So this will become -2 to +2, and finally add 5 to get the new range. So plus 5 plus 5. That's going to lead us with 5 minus 2, which is 3, and 2 plus 5, that equals to 7. So that is the new range. All right. Okay, so what about the operations here? Okay, so here we go. So I'm gonna start with a fresh set of values for the what's it called, for the from the cosine function. Okay, let me start by writing the key points, the fresh, not fresh values, fresh key points. All right. So number one. Okay. The point 0, 1, the point pi over 2, comma 0, the point What do we do? Um, what's the next point? Pi negative 1. The point 3 pi over 2, comma, 0, and the point 2 pi 1. Okay, so so guys, here is the thing. I really don't want to do all these divisions and multiplications, at least not for the x coordinates, because it's still gonna be a very weird way to get the number. So this is what we're gonna do. Actually, that's why we have the interval for one period. We're gonna use this. Okay. So here is the thing. Here's what we're gonna do. I'm gonna do a number line. Okay, I'm gonna do a number line. I'm gonna give some space right here. Do a number line where the lower bound of the number line is the lower bound in the interval for one period, that is 3 pi over 4, and the upper bound, that is going to be 5 pi over 4. All right, well, so let's find the value in between and the value in between, and those are going to be the y, the new x coordinates rather. Okay, so what is halfway between 3 pi over 4 and 5 pi over 4? Okay, let me show you the calculation for that. So halfway between 3 pi over 4 and 5 pi over 4, that's essentially finding the average of these two values, because that's going to be the number in between. 3 pi over 4 plus 5 pi over 4, that's 8 pi over 4. But instead of dividing this by 4, I'm going to multiply by 1/4. It would be easier. Well, not 4, right? It's actually by 2. Okay? So 4 times 2, which is 8, cancels this 8 right here, actually. So that's going to leave us pi. All right? So that is pi. All right. Now we need to find this value in between 3 pi over 4 and pi. And again, that's essentially the average of these two values between 3 pi over 4 and pi, and then divide everything by 2. Now, this calculation might be a little tricky because we would need to find least common denominators to combine the fractions together. Not 2, it's actually 4. Okay, so what is this going to be? 3 pi over 4 plus 4 pi over 4, isn't that 7 pi over 4? Okay, so that is 7 pi over 4, but rather than dividing by 2, I'm going to multiply by 1/2. And that's going to give us what as a result? Isn't that 7 pi over 8? 7 pi over 8, all right? So that is this value right here, 7 pi over 8. Now we need to find this point right here, or rather value, that is again by finding the average between these two values. Okay, so let me show you the calculation by hand. So pi plus 5 pi over 4, everything divided by 2. So this is the same as saying pi over 1, and I'm going to multiply numerator and denominator by 4, just the same way we did it before. So we can combine the numbers together. So 4 pi over 4 plus 5 pi over 4, isn't that 9 pi over 4? And rather than dividing by 2, I'm going to multiply by 1/2, leaving us with 9 pi over 8. Okay, so that is 9 pi over 8. Okay, so we may already go ahead and write the new set of x coordinates for the shifted values. Okay, that is 3 pi over 4 comma something. I'm going to show you this something in the y coordinates in a second. And then the next value, that's 7 pi over 8 comma the y coordinate, we will figure it out in a second, pi comma blank, 9 pi over 8 comma blank, and 5 pi over 4 comma blank. Okay, so let's find the blanks. Okay, remember what do we do to the y coordinates which are affected by the amplitude and the vertical shifting? Oh, so remember how we first multiplied the numbers by 2 and then we added 5? How about we do those two operations to this y coordinates? Okay, this number 1 multiply by 2 and add 5. Okay, 1 times 2, is that equal to 2? Add 5, is that equal to 7? 0 times 2, that's still 0 plus 5 equals to 5. Negative 1 times 2, careful, that's a negative 2. Negative 2 add 5, is that positive 3? And then 0 times 2, that's 0 plus 5, that equals to 5. And 1 times 2, which is 2, plus 5, that equals to 7. All right? And these are going to be the new key points on the transform function, which, yes, took us a lot of work. There's more. There's a lot more to do right here. All right, let's go to GeoGebra and graph these key points. I mean, to graph this function with the key point. Alright guys, so here we are in GeoGebra. So this time I plotted the graph of the cosine function, which is the parent function, but I didn't plot the key point. I think they're easy to see right here. Click, so I don't want to type them this time. Let me show you the graph of the function that we just plotted right here. 2 cosine of the quantity 4x minus 3 pi plus 5. Okay, so the first key point, which was 3 pi over 4 comma 7 from the work we did by hand. All right, is that the same? 3 pi over 4 comma 7, and then 7 pi over 8 comma 5. Is that the same value? Yes, 7 pi over 8 comma 5. And then pi comma 3. Is that 5 pi comma 3? Yes. And actually the 9 pi over 8 comma 5 and the point 5 pi over 4 comma 7. All right, so and notice in this case how we are graphing over one period. Now think about having to plot this by hand. It's simply not feasible. It's not an easy task. Let me see if I can do the x coordinate, change this to pi over, oh, I don't have uh, the keyboard ability to type all this. Anyway, so these are the points right here. See how hard and how tight would the window on the paper would be to just graph this function. So in some cases it's not gonna be an easy task. All right, well, let's go back to the notes and do one more exercise. All right, so back to the notes. So to graph one more trigonometric function, that is 3 sine of negative pi over 4x minus pi over 2 and minus 4. All right, guys, so in this case, you might want to take advantage of the even and odd properties of the trigonometric function, because do you see all of these negatives right there? I'm not gonna like it. You're not gonna like it when it comes to determining these intervals where we see the one period and all of that and the phase shifting. So number one, algebraically here, notice how the negative sign is common to both terms. So I'm going to factor it out. So that is sine, 3 times sine. I'm going to use bracket because I'm going to take the negative outside, and then I'm going to factor, that's pi over 4 x plus pi over 2. And well, let's recall the even and odd properties of the sine function. So let's recall that sine of negative x equals to negative sine of x. So that is, the negative sign goes outside, and that's gonna change the angle into a positive quantity. So I'm going to have this negative sign outside, and that is going to be equal to negative 3 sine of 4 pi, pi over 4 x plus pi over 2. Okay, and then, oh, don't forget the minus 4 right there. So I almost forgot it. Okay, so minus 4, minus 4. So we are going to have a big bunch of different transformations to this. Okay, so number one, a vertical stretching, and also that negative will flip the graph upside down. So let's label this as our A equals to, or our A simply, this is our B, this is our C, and this is our D right there. All right. So number one, let's find the amplitude. So for the amplitude, we will find the absolute value of A, and actually the absolute value is finally going to be useful because now we have a negative quantity, that is absolute value of negative 3, which is positive 3. All right. The period, which is P equals to 2 pi over the quantity B, which is 2 pi over the quantity B, which is 2 pi over 4. Be careful, because dividing by pi over 4 is the same as multiplying by 4 over pi. All right. And in this case, the pi's are going to cancel out, and we're going to multiply 2 times 4, which equals to 8. All right. What about the phase shift? The phase shift, again, that's by setting the angle pi over 4 x plus pi over 2, set it equal to 0, and well, that is going to give us, what's that? X, or rather pi over 4 x equals to negative pi over 2. All right. And then there's a couple of ways to isolate the x. I don't want to divide by pi over 4 because it's gonna look like very weird. I mean, look at this. No, and I don't have enough space to show that calculation. So instead, rather than dividing by pi over 4, I'm going to multiply by the reciprocal, which is multiplication by 4 over pi. All right, so that's going to lead us with the following. X equals to, cancel the pi's, and that's 4 divided by 2, which is 2, but it's also negative. So this graph will be shifted 2 units to the left. Do you see the positive sign right here? Means shifting to the left, and then the result right here is a negative number. All right, let's find the interval for one period. The interval for one period, what do? Bound the angle pi over 4 x plus pi over 2 between 0 and 2 pi. And let's solve the inequality here. I know that it looks ugly, but actually it's going to reduce to very nice numbers here. All right. Okay. So we will subtract pi over 2 on the 3 sides of the inequality. All right. Well, what is 2 pi minus pi over 2? So 2 pi, which is 4 pi over 2 minus pi over 2, that is actually 3 pi over 2. So that's going to leave us with negative pi over 2, 0 minus pi over 2, that's negative pi over 2, pi over 4 x less than or equal 2 pi over 2 minus pi over 2, that's 3 pi over 2. All right, so in this case, I'm going to multiply both sides, the 3 sides of the inequality by 4 to get rid of the fractions. Okay, and that's going to give us 4 over 2, is that negative 2 pi, less than or equal 4 over 4, that's pi x, and 4 over 2, that's 2 times 3, that equals to 6 pi. All right, and finally, to get the x by itself, divide the 3 sides of the inequality by pi. All right, so that is going to leave us with simply integers, negative 2, x, and 6, unlike the ugly numbers from the previous example. All right, well, so that's going to give us the interval for one period of the graph. All right, remember how ugly the previous example was, where we had to divide the interval 3 pi over 4 to 5 pi over 4, doing all these side calculations? That's because these numbers are fractions. Now, in the case where these are integers, well, the work is going to be a lot easier. Well, number one, let me start with a fresh set of key points for the sine function. So the sine function points are going to go from 0, 0, what else? 1, 1. Wait, no, not 1, 1. Pi over 2, 1. Pi 0. What else? And that's going to be 3 pi over 2. 3 pi over 2 negative 1. And 2 pi 0. All right. Also, before we calculate the new points, actually, something I forgot to do is to calculate the new range of the function. Because again, coming back to the previous example, the amplitude and the vertical shift affect the range of the function. And I'm going to start with the range of negative 1 to 1. In the previous example, we multiplied by the y values by 2 and then added 5 units. In the next example right here, what we're going to do, so here let me highlight so you can see what we're going to do. So we will multiply by negative 3 and then add or subtract 4 units, add negative 4 units or subtract 4 units, either way. So, and again, order matters because this is multiplication, this is addition. The multiplication goes first. All right. Well, so let me start with the range. So new range. So the new range, which starts between negative 1 and 1. Okay, I'm going to multiply both numbers by 3, by negative 3. So times mine by negative 3 times negative 3. Okay, so this is going to give us a new set, or rather a new interval. That is a new range. Negative 1 times negative 3, be careful, that is negative 4, positive 4. All right, and 1 times negative 3, that is negative 3. But actually, guys, I don't think this makes sense to read, because intervals of numbers are always meant to be read from smaller to large, not from large to small. So fix this by simply reversing the order. Okay, and lastly, what do we do? Subtract 4 units to both. That is, and that's the little trick right here, the little common pitfall when having first the larger number and then the smaller. That doesn't make too much sense. So let's subtract 4 to both endpoints of the interval. So that is going to be negative 3 minus 4, that's negative 7, and 4 minus 4 equal to 0. All right, so that's what we're going to get for this one. All right, well, so number one, let's come up with the new points. Okay, remember that number line for the new x values, starting at negative 2 and finishing at 6. So negative 2 and 6. These are easy to get by by doing in our head, if you will. So halfway in between negative 2 and 6, that's actually positive 2. If you want to write this down, that's fine. All right, that's because, okay, negative 2 plus 6 divided by 2, that's 6 minus 2, which is 4 over 2, which equals to 2. Right now, halfway between negative 2 and 2, I think it's easy to see that this is 0. And finally, halfway between 2 and 6, that equals to 4. So the new x coordinates right here are going to be negative 2 comma blank, 0 comma blank, 2 comma blank, 4 comma blank, and 6 comma blank. All right, well, so how do we find the y coordinates? Remember what we did here? Multiply the y coordinates by -3 and subtract 4. Okay, so let's do this in our heads. Okay, one at a time. 0 times -3, it's still 0. Minus 4, that's -4. Okay, 1 times -3 is -3. Minus 4 equals -7. 0 times -3, it's still 0. Minus 4, that's another -4. Okay, and what is that? 4. -1 times -3, that is +3. Hold on again. -1 times -3, that's +3, minus 4, is that -1? Yes, -1. 0 times -3, that's that's 0 actually. Minus 4 equals to -4. So these are our new points that we will plot, the key points for the shifted function and transform function. Well, I've just realized I did a silly mistake right here for, so -1 minus times -3, it was not 4, it's actually +3. So that changes, and that's actually -1. All right, so that actually agrees with what we have. So sorry in advance if that caused any confusions. Okay, so now let's plot this key points to come up with the graph of the transform function. Let's go on GeoGebra for that. Alright, so here we are in GeoGebra, and again I didn't graph the key points for the sine function. So this is one period of the sine function, and again I didn't use pi's and pi's over 2 because actually the shifted function, look how it looks like, looks kind of weird, and it actually has key points that do not contain any pi's. Alright, so that is -2, -4, 0, -7, 2, -4, 4, -1, and 6, -4. Those are the 5 key points we calculated by hand in the notes right here. And again, that's the interval for one period, -2 and +6. So see how that goes. It goes between -2 and +6. I also, when I type the function over here, which is a big typing, see the inequality for the one period between -2 and 6 does not involve pi's this time. And this is how we graph a couple of trigonometric functions containing all kinds of transformations. And as you can see from all the work we did, it takes a good minute to get all the properties such as amplitude, period, phase shift, and even though we are not required to find this interval for one period, I highly encourage you to write it down so you can see what's the window or the interval where you will see that one period that we're looking for. Right, that's one, and that was the previous example, which again required quite a bit of work. So this is the end for the video for graphing sine and cosine function and its transformations, all of its transformations.